Next, let's talk about a very important high school experiment, the laboratory preparation of ammonia. There are many methods for the lab preparation of ammonia, and we'll cover them one by one. Why discuss this? It's not just about equations, the focus is on equipment selection and use. You must be clear on the key points of each topic, which is the selection and use of equipment. Let's take a look. First, the solid heating method for ammonia. As we just mentioned, ammonium salts can react with bases to produce ammonia. So we can heat a mixture of solid ammonium chloride and calcium hydroxide, which will produce calcium chloride, water, and ammonia. No problem, right? Now, for solid heating, which way must the test tube mouth be tilted? Tilted slightly downward. Because they're all solids. Okay, next, since water is produced, we need to dry it using soda lime to dry the ammonia. Next, since ammonia is less dense than air, we use downward air displacement. Think about it. As ammonia rises, air also moves downward. To prevent this airflow countercurrent, we use a cotton ball. But actually, the cotton's role is to prevent ammonia from escaping into the air because it's toxic. You get what I mean? Okay, let's write its reaction equation. Ammonium chloride and calcium hydroxide. For under heating conditions, produce calcium chloride, water, and ammonia. No problems there, right? I've given you the key points. You must be clear on the equipment focus. Okay, next is the second one. Since concentrated ammonia water decomposes easily, I can directly heat it to produce ammonia gas. No problem, right? You understand? Okay, let's look at some equipment. First, the round-bottomed one is called a round-bottom flask. A round bottom flask can't be heated directly, so we need to place an asbestos net under it. Okay, next, its principle is actually just ammonium hydroxide decomposing when heated to produce ammonia gas and water. But this one, we don't usually use it. We generally don't use this reaction. We use the first reaction the most, and then the third one I'm about to explain. Okay, let's look at the next one. The previous ones involved heating, right? Heating makes the experiment, well, potentially dangerous. So how can we do this without heating? It also uses the thermal decomposition of concentrated ammonia. But how to get heat? Concentrated ammonia contains water. If a substance releases heat when dissolved in water, could it provide the heat? Am I making sense? For example, I use solid sodium hydroxide. What happens when sodium hydroxide dissolves in water? It releases heat. This heat can then promote the decomposition of the concentrated ammonia water. Got it? So I should add concentrated ammonia water dropwise to the solid sodium hydroxide. Solid sodium hydroxide should be placed in the round bottom flask. Do you understand? So the principle of the first one is that ammonia monohydrate decomposes when heated, producing ammonia gas and water. The sodium hydroxide here acts as an exothermic agent, providing heat. Okay, so what if we use concentrated ammonia water and solid calcium oxide? The first key point is, what happens when calcium oxide dissolves in water? It's exothermic. It will absorb water, right? It absorbs water to become calcium hydroxide. The principle is like this. Calcium oxide will absorb water to produce calcium hydroxide. During the process of calcium oxide dissolving in water, is it exothermic? The heat released will promote the decomposition of ammonia monohydrate, right? But can the final product still be calcium oxide? No, so in the equation, calcium oxide should react with the ammonia monohydrate. No problem, right? So what should be produced? Calcium hydroxide and ammonia gas. Can you see that? The first one is heated because sodium hydroxide provides the heat. The second one is because calcium oxide dissolves in water, so I won't write heating for the second one. Understood. Okay, good. This is our generation apparatus. All the key points are here. Actually, the first one is tested the most. Next, let's talk about the collection and drying apparatus. Since ammonia gas, well, it's an alkaline gas. So we can use a neutral desiccant or an alkaline desiccant. Right? For a neutral desiccant, we mentioned calcium chloride when studying sulfuric acid. And for an alkaline desiccant, soda lime. But in this particular case, we can only really use soda lime for drying purposes, not anhydrous calcium chloride. Why? Because if anhydrous calcium chloride is used, they will react to form calcium chloride octammoniate. That is, ammonia will react with calcium chloride to form calcium chloride octammoniate. Can the ammonia still be dried? It's already reacted into another substance and you won't be able to collect it. Do you see what I mean? So anhydrous calcium chloride must not be used. We use soda lime here. Does that make sense? Can we use concentrated sulfuric acid? No, because what would it do? It absorbs ammonia and reacts with it to form ammonium sulfate. It's an acid-base neutralization, okay? Now that we've covered drying, let's talk about collection. Since its density is lower than that of air, we should use the downward displacement of air method. It must be downward displacement of air, okay? Now, if it's just a test tube, that's the simplest way, but what if I give you a multi-purpose bottle instead? If the density is lower than air, it should be short tube in, long tube out to push the air down, right? So it should be in through A and out through B. I hope you can see that. One last point, let me ask you, is ammonia toxic? It is, right? So in the end, what must be done? Tail gas treatment. Okay, let's continue. Before we handle the tail gas, let's test it. How do we test for ammonia? Either of two properties will work. First, it can turn moist. Red litmus paper blue. That's one test, right? Second, what can it do? When it is in close proximity to concentrated hydrochloric acid, for example, close by, it produces white smoke. What's produced? Ammonium chloride. Got it, class? Okay, good. Next, tail gas treatment. Ammonia is highly soluble in water. So it easily causes what? Back suction. What we need to learn here is how to prevent back suction. That means all the devices you'll see next are designed to prevent back suction. Let's discuss how they work. The short in, short out method prevents it. I don't need to explain that because even if pressure drops, the liquid stays in this bottle and won't be sucked into the left side, right? If it can't enter the left side, it prevents back suction. Now, let's look at these two instruments on the left. They both have a large bulb, see? Both the inverted funnel and the spherical drying tube have a large bulb. If water rises, it enters this large bulb, right? When water enters the bulb, the water level in the beaker also drops. Do you follow me? At this point, doesn't the opening reconnect with the atmospheric pressure? Then what happens to the liquid? It falls back down. So, will the liquid be sucked back into the left instrument? No. Thus, this process prevents back suction. The second one works on the same principle. If you understand these three, I'll focus on the fourth, which is the most important. Everyone mark this as a key point. And it's a very common exam topic. First, for ammonia tail gas treatment, what should absorb it? Sulfuric acid, because ammonia can dissolve in sulfuric acid. Since ammonia reacts so readily with sulfuric acid, back suction will definitely occur, so we must prevent it. So how does this device prevent back suction? Look, when ammonia enters the carbon tetrachloride, it's all bubbles. Does it dissolve? No. Since it doesn't dissolve, it travels up with the bubbles. The bubbles rise, right? So during this process, is the pressure inside the tube affected? No. Moving on. When it reaches the upper layer and is absorbed by the dilute sulfuric acid, does that absorption process affect the pressure inside this tube? No. Therefore, the tail gas treatment is effectively carried out in the upper layer. An anti-suckback operation was carried out below. Does that make sense? It does, right? Good. Now, here is how this might appear on an exam. Beaker. Benzene, water. Can water absorb ammonia? Yes, it can. It certainly can. All right, ammonia gas is introduced. Is this setup okay? Remember, it is not. Why? Because benzene is less dense than water. So benzene, which layer is it in? It is in the top layer. This means the apparatus is drawn wrong. If we were to draw it correctly, this should be water. This part should be benzene. Makes sense, right? Now, if ammonia gas flows in, wouldn't that cause an instantaneous drop in pressure inside this tube? Because it would suck the water right up into it. See what I mean? It affects the pressure inside the tube, causing an instant drop, which leads to suckback. So this setup won't work either. Do you see? What must it be? A liquid with a higher density than water. A liquid denser than water. All right. So that is the anti-suckback procedure. Okay, so up to now, we have covered the lab preparation of ammonia, drying, tail gas treatment, absorption, and testing. Now, let's add one more important point. Get your red pens out, class. In this spot, we can use ammonium chloride and calcium hydroxide. But what about this? Sometimes you're asked if you can simply heat ammonium chloride alone. Can you? If I just heat ammonium chloride, it also produces ammonia and hydrogen chloride gas, right? Then, if I use soda lime to absorb the hydrogen chloride, wouldn't ammonia be released? You might think so, right? But this does not work, and I will tell you why. Because hydrogen chloride gas and ammonia can still react with each other. Doesn't the temperature drop right here? Right? Once the temperature drops, they can react again and turn back into solid ammonium chloride. Now, if it turns back into solid ammonium chloride, have you actually produced any ammonia? No. So remember, using the decomposition of ammonium chloride alone won't work. You can use ammonium chloride and calcium hydroxide. That works. But if you say simply heating ammonium chloride to produce ammonia, it is not allowed. Did I make that clear? Okay, good. So we have finished the preparation part. Let's look at the questions. Exercise 1. Which statement about the lab preparation of ammonia is correct? A. Although ammonia water decomposes when heated to produce ammonia, can we heat concentrated ammonia water in the lab to get it? Yes, we can. We just discussed that, right? So A is definitely wrong. Option B. Concentrated sulfuric acid is often chosen as a drying agent. No, because ammonia and concentrated sulfuric acid will react, right? You won't dry it, it will be absorbed. C. Ammonia can be collected by downward air displacement or water displacement. No, it is highly soluble in water. Option D. Use soda lime. What is soda lime? Sodium hydroxide and calcium oxide. Replacing slaked lime. What is slaked lime? Do you know? Slaked lime is calcium hydroxide. It can speed up the reaction rate. Let's see if it works. First, ammonium chloride and sodium hydroxide can react to produce ammonia and water. The water can be absorbed by calcium oxide to become calcium hydroxide. Then the base produced can react with ammonium chloride again. Does that make sense? So it provides a steady stream of hydroxide ions to react with ammonium ions to produce ammonia, right? So speeding up the reaction rate is no problem. Option D is correct. Now, question 2, the choice of apparatus. Using apparatus A to produce dry ammonia. Concentrated ammonia water is mixed with quicklime. Quicklime dissolves in water and releases heat, so the concentrated ammonia water decomposes to produce ammonia gas. Ammonia and water are produced, and the water is absorbed by soda lime, so it can produce dry ammonia, no problem. Option B, using apparatus B to collect and measure the volume of gas produced by the reaction of copper and concentrated nitric acid. Can we calculate it? No, we can't. Why? First, concentrated nitric acid is volatile and will dissolve in water. Second, nitrogen dioxide will react with water. So the second one is definitely wrong. Using apparatus C to remove hydrogen chloride from carbon dioxide, what saturated solution is used? Sodium bicarbonate. Because if you use sodium carbonate, carbon dioxide will dissolve, right? Okay, C is also wrong. Using apparatus D to absorb ammonia and prevent back suction is definitely wrong. The answer is A. Didn't I just explain D to you? Because at this point, it's extremely soluble in water, so it will suck back immediately. Your benzene is useless here, right? Okay, next question. Below are the apparatus and reagents for laboratory preparation of ammonia. Which one is wrong? You can't directly heat ammonium chloride, as we've discussed. A is wrong. Option B is fine. Concentrated ammonia water with calcium oxide, right? This calcium oxide dissolves in water and decomposes to produce ammonia. For calcium hydroxide and solid ammonium chloride, the mouth of the test tube should tilt slightly downwards, so option C is also wrong. Option D, concentrated ammonia water. The mouth of the test tube tilts slightly upwards. For liquids, right? Tilt it slightly upwards. Ammonia and water are produced and the water is absorbed by soda lime. D is fine. All right? So the wrong ones for this question are A and C. You must be clear about the key points being tested. Question 4. 1 is the generator. No, you can't use solid ammonium chloride. B. 3 is the generator. Producing ammonia, this works, right? Yes. 3 is fine, right? Mixing solid and liquid. 2 is the ammonia absorption apparatus. Absorption is fine, but won't it suck back immediately? You didn't set up the anti-back suction part correctly, did you? It needs to absorb from the outside. Does that make sense? Okay, so C is wrong. Option D, 4, is the ammonia collection and testing apparatus. Let's talk about collection first. When you collect ammonia, since its density is lower than air, this tube must go where? To the top, because you start filling the ammonia from there. No problem, right? So this part is wrong. Second, the testing apparatus. Moist red litmus paper turns blue. Placing it at the mouth of the bottle can test it. No problem. The second half is correct, but the first half isn't. So the correct answer for this question is B. Okay, so that's all for the preparation of ammonia. Actually, this lesson's content is quite substantial. From the properties of ammonia, right? Ammonia is highly soluble in water, the fountain experiment, to the laboratory preparation of ammonia and common issues when choosing the apparatus. Then I explained the properties of ammonium salts, okay? Finally, the testing for ammonium ions. This is the key content of our entire lesson. The content of this lesson isn't hard. It's more about reviewing 9th grade chemistry. Did you notice? Okay, that's all for this lesson.